check. Okay, now it's on. Okay, I was even muted. Damn, I was even muted. Okay, now we actually on here. Now we actually up in this. I just want to figure out how to see it on my monitor though. How do I actually see edit panels, crack, physics, chemistry, X account? Yeah, it says I'm offline. Wait a second. What the fuck? Come on, bruv. Okay, let me see my YouTube. Let me see, view your channel. Surely it should say I'm live. I'm live. Okay, fantastic. Man, I typically stream to X and to Rumble. I got rid of my X account. Or like, I got rid of premium and all. That's live. Okay, let me see it. Is the quality really that dog ass? Nah, I can go to 1080. And then it ain't as bad, but it's still kind of bad. Okay, yeah, that sounds pretty good and everything. I just want to check out the quality of the sound. All right, let's see what the video looks like when I switch over to this. Let's see how bad this is. I hate this little moment of checking the stream every time. I wish I could just start up and get straight into what I'm trying to do, but I got to make sure it looks nice. A bit of a delay there. I got to figure out how to see myself on here. Community, go ad free. You cannot call in to join your stream. Yeah, does this actually look decent? How do I, bruh. Audio only. I want to go full screen on this. I guess that's all I can do though. Quick actions. I wonder what that does. Edit stream info. I see. What does that do? Aren't available during the first few seconds of stream. Wait. Shut up, bit ass. Oh man, there's a lot of different mechanics to Twitch streaming, isn't there? Man, whatever. I guess I got it recording right now. All right, we're gonna continue forward. I hope that everything's going well, but whatever. All right, I'm gonna take this off. We don't need that. Okay, so I'm gonna hop over to the first problem. It's going to be like exploring impulse response of these various components. So our two components in particular that we really want to know is what's happening with is here, let me get rid of that. Fuck. Okay, we'll just leave him up. I wonder, and then on my restream, I should be able to see the chat, all chats. Okay. Man, we're still live, right? Connection, Prime Gaming, channels and videos, profile, channels and videos. Okay, so there's the creator dashboard, and this is where I'm going to find my stream. Stream manager. Boom. Okay. Very good. Oh, I can see my bitrate and all. Oh, that was looking like garbage. Okay. All right, let's get a little something drawn on here. Why does this keep having a problem focusing? Okay, wait, I'm just going to deactivate this camera real quick because it's actually having problems. Give it a little bit, give it a little bit. Here, I guess I could have went like this so you guys can see me a little bit better so it's not quite so boring. Okay, well then now I can't change the properties of that camera without being in it. And a different one. All right, here we go. Activate. Oh, and it's having super big problems. Configure video. Oh my goodness. Focus. It's automatic focus. Why is it all the way up though? And then it gets all weird. Manually focus? Let's try that. Now it shouldn't change. It should always stay focused on this, huh? All right, perhaps that'll work. Perhaps, okay, we're having technical difficulties considering that this is a technical stream. We're going to find a solution, okay? No matter what, we will always find a solution. Here, let me look up the definition of this word. Because I don't want to use it in the wrong definition. We don't want to sound like an idiot, all right? A faculty or property distinguishing a person or class. A faculty or property. I would say, yeah, that problem solving is our prerogative as engineers. That's the word I was looking up, prerogative. But okay, now I understand what it means. I will never forget. Okay. Let me get out of here. What's up, everybody? Welcome to the stream. I don't know if I have any viewers, but let's hope. Let's hope. All right, we're going to get into the impulse response. So let me draw out our circuit real quick. It's going to look like this. We're going to go straight there to the inductor. Like this. This is our resistor. And then straight to our inductor. And you know, we haven't really looked at any inductors yet, but we are going to now. And then to our capacitor. Ah, man, that's good enough. Really trying to get a good drawing so I can please you guys. So there's some level of satisfaction, some level of interest into the drawing itself. And then we have a voltage source, Vn. Yes, and it's time-dependent voltage source, so it changes over time. Except we're going to be working with an impulse. So it's going to go from 0 to 100. Well, not really 100, but 0 to some magnitude. In this case, it's 1 volt second is the unit of impulse. And this means that it's not like... I don't know. I guess I'm not going to describe it. I'm just going to... Or I will describe it in just a moment. We'll do everything in a timely manner. In somewhat of a chronological order, so it makes a little more sense. Let's continue to work with it, and then we'll explain things. So we're just labeling everything that's important when we're doing the schematics. Man, here, let me see something. Perhaps getting rid of some of the light might help with the exposure. It seems to keep having trouble. It's like nothing is staying perfect. Nothing is staying perfect. You know, one issue I was considering about streaming on Twitch is like, I don't know how many people are really going to be interested in learning about electronics and physics and stuff. Perhaps there will be. What about like my lag? Am I doing okay? Streaming for 2. Yeah, that's probably me though. Okay, I don't know. All right, let's continue forward. Positive, negative, we're going to always label that. We're going to label our positive and negative to understand the flow of the current. This is also time dependent. Because our input is time dependent, everything else, any other voltage is going to be time dependent. Positive, negative, VR1, R1 of T. Because it's a time dependent function. Okay, so consider the circuit shown above in which Vn of T equals 1 volt seconds. Okay, so we're just going to write that down. We're going to put out all our knowns so that it makes it easier for us to find our unknowns. We want to have all of the parameters that have already been defined by the problem given. We want to have those laid out so that we can stay well organized, and this will assist us in deriving the solution to the problem. Okay, so our impulse looks like this. Vn of T equals what? Just 1. 1, and then this is what the symbol for the impulse function looks like. It just looks like that, of T, and then volt seconds, but we're just going to put Vs like that. That's volt seconds. That is, Vn is a unit impulse at time t equals 0. Okay, so before time equals 0, there's nothing happening, no input. Right at time t equals 0, we go straight to 1 volt. 1 volt. Like within no time. That's the whole thing about the impulse, is that it's not really like it happens instantaneously. That's the thing about the impulse. It happens instantaneously, and so we're going to see how the circuit responds to an instantaneous jump in voltage. Okay. At time t equals 0 in the circuit. Okay, so now we're going to define these parameters of our components, such as L is the inductance of our inductor right here. L equals 5 millihenry. millihenry. R1 equals 10 ohms. R2 equals 10 kilo ohms. Okay. R1 equals 10 ohms. Here, we'll write it. Yeah, R2 equals 10 kilo ohms. And then C equals 33 nanofarads. That's our capacitance. 33 nanofarads. All right, and then we'll kind of like, once we start doing the calculations and crunching the numbers, I'll give you some insight into the quantity of those units, such as like nano, milli, and kilo. I'll give you insight into the quantity of those units, such as like milli, for instance, is times 10 to the negative 3. Okay, like we'll look at that in a moment. Note that since the circuit is driven by an impulse and there is no other source of energy, the capacitor voltage and inductor current at t equals 0 will be 0. The capacitor voltage and inductor current at t equals 0 will be 0. Okay. So this is to say, we're also going to define that. We're going to put that down. So the voltage, VC, the voltage across our capacitor as a function of time, at t equals 0. That's why we're putting 0 in the parentheses. Normally a t would be the placeholder, but like we're plugging a value in for t, so we're just going to put 0 there. So VC of 0 at 0, once the impulse happens, equals 0. And then IL, the current through our inductor at time 0, also equals 0. Just meaning like an inductor current at t equals 0 will be 0. I'll explain as to why that is the case. Let's see where we at. What is the value of VR1 of t at t equals 0 negative in volts? Okay, so the question is, the first question, here we'll label it with Roman numerals. We're going to say, what is the value of VR1? So the voltage across R1 at t, at just the instant before t equals 0. So, okay, so let's, you know what, before we do this, let's define our impulse and let's put it on a graph. Let's like define it graphically so that we get some insight into how this is actually operating. But cool. All right, I appreciate y'all being here. Man, I don't know, actually that's quite disappointing. I don't know what it's going to take for me to like actually build some motion on here. Man, let me see. HD is good. I mean, it's like good enough, but the quality still isn't. It's not good enough. It's not good enough in regards to my paper, the paper quality. I feel like my camera quality is quite decent. Maybe not even. Nah, that actually kind of looks like garbage on there too. I'm gonna have to look that up. I'm gonna have to do some research on how to get better quality. It just must be my stream. It's just my stream, my streaming software not putting out the best quality to the platforms that I stream on. So, but whatever, it is what it is for now. Okay, let's continue forward. So we're going to define the impulse graphically. So if we're to draw a graph here, this is our x-axis, right? That's our y-axis. Our y-axis is going to be the voltage. This is going to be our time axis. Just like that. Put some arrows just because it looks nice. Okay, we're going to define it at 1 volt. You know, we're not working with huge numbers here. But you will see that by applying an impulse to the circuit we're about to analyze, by applying an impulse to this circuit, you get some incredibly large numbers. And, you know, it's not the way the real world operates because nothing happens instantaneously. Nothing really happens instantaneously like that. And also because of physical properties such as like resistance and things like this, it's like you can't actually jump from 0 to 1 volt instantaneously. There's somewhat of a delay because of like parasitic capacitance, parasitic inductance, things like this. And actually the next problem we're about to do today, we're going to take a look at parasitic capacitance, and we're going to do a time analysis of the circuit and see what the delay is. The delay in rising from 0 to whatever our input is. I think it's like 5 volts or something like this. But whatever. Okay, so right here, everything right here, that's all zero. Anything before t equals 0, right at this point, okay, everything is 0 volts, no input. Everything after is no input. Okay, so right here, just at t equals 0, we're going to get this impulse. So I'm trying to darken it, okay, to show. That's going to be our impulse. And so that's going to be, I guess maybe we could define this like this, just to give some insight that this is the impulse function. That's what it's noted as. That's the impulse function. So just keep that in mind. And impulse of 1 volt. Okay, 1 volt second. All right, so... Okay, and then what I was about to define before that was what? Oh, yeah, the first problem of... Yeah, the first solution to the first problem. So the first problem, again, is what is the voltage across R1? Okay, so the voltage across R1. So VR1 equals at... VR1 of t, right? It's time dependent. But we're going to plug in something for t, and it's 0 to the negative powers, like essentially how you'd say it. And what that means is just like when you have a negative, it means just the instant before t equals 0. If it were a positive, it'd be the instant after t equals 0. So we're just talking about very, very minute time segments before or after t equals 0. So just moments before t equals 0, we have no input into the circuit. There's no voltage. Therefore, there's no current. Therefore, the voltage across R1 is just going to be 0. The impulse hasn't occurred yet, just moments before. Now, what is the value of the voltage across R1 at t equals 0 positive, which is just a moment after the impulse had occurred? Okay. So VR1 of 0 positive equals. Okay, so now we're actually going to start crunching some numbers, get into the calculation. But a lot of this right here actually comes down to like a logical analysis. You know, it's like not everything required to solve this problem is going to come down to numbers. You need to know how it operates and things like this. So we'll kind of talk through that as we get to that point. So continuing forward. Okay. We want to know the voltage across R1 just moments after the impulse had occurred. Okay, so we have a voltage impulse. You could have a current impulse also, but we have a voltage impulse. Therefore, the voltage impulse is going to define the magnetic flux, because voltage has a relationship to electric fields, and these electric fields have a relationship to magnetic flux, in particular to the inductor, like magnetic flux, inductance. So an inductor, okay, let's just explain a little bit. An inductor is a coil of copper. It's just wound around. You know, perhaps I don't really have nothing right on hand to show you, but it's here, let's look it up. Let's look up an inductor. Boom. Okay, let's look up an inductor to give you some insight. So, okay, here we are with the inductor. Oh, nothing showing. No, that's good. All right, let's just think of this one in particular because this is the most like fundamental inductor. This one has an iron core, ferrite core, and that's going to change the properties of the inductor. But let's just think about an air core inductor, just like this one. Okay. So that's what it looks like. It's just a coil of copper. It could be any conducting metal, but it's like or a conducting material, I guess. I wonder what it would be like to make an inductor out of a semi-conducting material, if that's even possible. But it's like, I don't know, it seems really interesting. Anyways, so when you apply, I guess we could think about it even as a current. Okay. When a current flows, like a current, amps is the unit of current. Current is electrons flowing through this inductor. When a current flows through the inductor, a magnetic field is generated. And this magnetic field builds up as the current flows, and then when the current ceases, the magnetic field breaks down and puts out current in the opposite direction of which the initial current started. and then it pumps current out in the opposite direction. Okay, so that's kind of like a little insight into its physical properties, the way it operates. Now, we have a relationship, I'm trying to think. Okay, so now we have this voltage impulse. And this voltage impulse is going to induce a magnetic flux through this inductor. Yes, here, let's write this down right now. Let's think this through. Let's think this through and get a complete understanding of what's happening here. Okay, so I know that the current through the inductor is equal to this magnetic flux divided by the inductance, which is, the inductance is just like the inductance is defined by the physical properties of the inductor. So like going back to this picture, it's like the number of turns it has, it's the thickness of the wire, it's the length of it, it's things like this. It's what, it's made of copper, whether it has an iron core or no iron core, stuff like this. This is going to determine the inductance. Okay, so I know this is true, that the current through the inductor is proportional to the magnetic flux and improportional to the inductance. Okay, so I know this is true. Now, what I'm trying to think really is how to explain why the voltage impulse is what, like the voltage impulse's relationship to the magnetic flux, because I know it's true, but I'm just trying to think about how to explain it in simple terms. Let's run through a scenario real quick. If this was a current impulse, then this would define not the magnetic flux. It doesn't have a relationship to the magnetic flux through the inductor, but it would have a relationship to the charge buildup on the capacitor. And this is the way we would define things if it were a current impulse. We would define it by the capacitor, not the inductor. But this time we have a voltage impulse, and so we're going to define it by the magnetic flux through the inductor, and this is going to give us necessary relationships to find the answer. Okay, so I'm just trying to think. Like, I understand that, through studying physics and stuff, you'll learn that alternating electric flux induces an alternating magnetic flux. And this is the reason why generators produce electricity. I don't know, I'm trying to think of other phenomena to apply it to, but I'm just trying to think about how it plays in this scenario. That would be what it is then. We have the voltage impulse, and this is going to directly deposit, I guess you wouldn't say deposit, but it just induces the magnetic flux because of the relationship between electric flux and magnetic flux. It directly induces a magnetic flux across the inductor. But it does not define the charge deposited onto the plates of the capacitor. It just doesn't. Okay, I know this is accurate. I know this is true. So again, this is the current through the inductor is proportional to the magnetic flux over the inductor divided by the inductance. Okay. They are positive. Okay, that's true. So now if I were to take this, so IL. Okay, so now we want to know the voltage across to R1. And by Ohm's law, we know that I times R equals V. Okay, that's Ohm's law put simply. So here, I'll put this as a capital. I don't like how I have lowercase and capital in there. So I times R equals V. Okay, so IL, the current through the inductor. Now, because these two circuits right here, or these two branches, are decoupled when we are doing an impulse response. They don't play much part with one another because we apply the impulse, and then I guess I don't know why. I don't know how to describe why they're decoupled. But they are. Maybe they do it for simplicity reasons. Yeah, it must be simplicity reasons, because if they weren't decoupled, then it'd become a resonant circuit with a decay defined by the resistance. And yeah, to do a resonant analysis is quite a bit more complex. So all right, let's continue forward. So IL times R1. Okay, so now considering that these are decoupled, we're gonna have the same amount of current flowing through both of these components, and the current is going to be defined by the magnetic. Yeah, we're gonna define the current by the inductor, which, as we already described, was the current through the inductor is proportional to the magnetic flux divided by the inductance. Okay, so IL times R1 is going to give us VR1, and now that's what we're looking for, right? That's the solution to our problem. So now we just plug in this magnetic flux divided by L multiplied by R1 equals VR1. The magnetic flux, because we have a voltage impulse, is directly proportional to the voltage impulse. So it's just simply 1 volt second in this case. 1 volt second. And now we're going to use this parameter to define the voltage across the capacitance and things like this. But since it's a voltage impulse, it doesn't directly affect the capacitance. The capacitance will be affected by... We'll take a look at it in a second. Okay, so this is the case. So now we're just going to plug in 1... I guess we'll put our units to 1 volt second divided by 5 millihenry multiplied by, 10 ohms. Okay, is going to equal VR1. And this itself equals... Let's see, yeah, keep that there. Man, my my exposure is too high, or my brightness. I think it's my exposure. What if I turn down my brightness? How much better does that get? I mean, a little bit. I want to turn down my exposure, but it's like I've already gotten so far. Okay, I don't know. I'm just gonna leave it there. Because it really don't look that bad, but I mean, like, can't really see. Yeah, bro, that's the thing. When I stream on X, I actually have some viewers. Right now, I ain't got shit. I ain't got shit for viewers. Which, I mean, is it super important, I guess? But damn, come on, everybody, get up in here. Let's go. Okay. But anyways, let's do this calculation. So we have 1 divided by, never mind, I just do it like this. 5. Okay, so e to the, so you can't see that at all. Fuck that. Fuck that. We're going to make it right. And then we'll turn up the brightness. Heat warning? Oh, hell no. See, now it's too dark. That's way too much. Oh my gosh. That's kind of better. Nah, let's see how it looks on here real quick. Man, I hate messing with this stuff. I got a subscriber? What? That's awesome. I don't even remember when. I didn't even know that happened. Okay. How's that look? That looks okay? Man, it's so dark now. Oh, fuck. It was too much exposure. Okay, but anyways, 5 millihenry. So we got 1 divided by 5 E. I'm going to use E, but you could also say times 10 to the negative 3. But I'm going to use E, negative 3. Another method of doing the same thing. We got 200. We're going to multiply that by 10 ohms. And that's going to give us the voltage across the resistor, R1. Isn't that crazy, right? So we applied an impulse of 1 volt second, and we're going to get a response of 2,000 volts across R1. Volts. All right, boom, just like that. Okay. No, that's kind of decent, right? You can see that decent. Yeah, that looks okay. Yeah, it looks okay. The quality's not great, but you can still make out all the letters and stuff and the subscripts, so that's the most important part. That's the most important part. Yeah, bro, I canceled my X Premium account. I guess maybe I'm gonna have to get it back because I want to stream on there. You know, unless I build somewhat of an audience on here. I also want to, I'm going to take these videos, I'm going to cut them down and get to the most important parts. And I'm going to post those too. But, alright. But, no ass. Let's get back into it. I wish you guys were here in the chat. I wish you would say something. We should quit playing around. Being a bunch of knuckleheads. I forgot what I was doing. Okay, so that's the answer to that question. What is the value for VR1 of t at t equals 1 millisecond? Okay, so now we have an actual particular specific time. What is the value for VR1 of t at t equals 1 millisecond? Okay, so now we're going to have to define an equation which has our independent variable being the time, and we're going to solve for our dependent variable voltage across R1. Okay. So what's that going to look like? What is that going to look like? What is that going to look like? 1 millisecond, the LR1. It's going to be an LR circuit or RL circuit indeed. Trying to think. Yeah, I'm pretty sure that's it. So it's going to look like this. So let's draw it in a different model. We're going to simplify it, right? These are decoupled. These two branches are decoupled. So these two branches are decoupled, and this is after the impulse. This is actually 1 millisecond. So it's a good amount of time after the impulse. Our source is going to go away, and it's going to look like this. With just the inductor right here. Alright, so we can say that these two elements are in parallel. They're in parallel. They share the same current this way, current this way, coming out of this node right here. They're equivalent. Indeed. Trying to think what else do we need to define? Right, at t equals 1 millisecond. Okay. Right, so we have, do we want to define it by the voltage? By the voltage? Is this what we want to do? Man, is that bright enough? Can I get some more light on it? Look at how that's like, why is it so much light? Why is this light so bright? Fuck. Man, I'm really having a difficult time here. Come on, you guys, get up in here, get up in the stream. Need some more people up in the stream, tell your friends. Tell them about it. Come learn about engineering and science. Learn about physics. We're literally doing physics here. So, I mean, who else does this? Who else streams physics? I mean, come on now. Give me a follow, like the video, you know, you heard, whatever. Okay. Alright, so this is what we're doing. I'm just trying to think, are we going to define it by the current or by the voltage? I feel like by the voltage is what we're going to do, but yeah, by the voltage, which that equals that. No, that equals that. Okay, so let's define these, like, I forgot the term for them. Constitutive. Let me look it up real quick. Constitutive laws. Inductor. Constitutive. Let's see what this word is. What? Constitutive. Yeah, that'd be how you say it. Constitutive laws. Describe the behavior of devices such as capacitors and inductors based on their state or history. Okay. Alright, very well. Constitutive laws. Okay, so let's write down the constitutive law for the inductor. So we can write it down like IL equals 1 over L times the integral of VL. Or we could say that VL equals the derivative of IL. Or, yeah. We say L times the derivative of IL over with respect to time. With respect to time, it's a derivative. Okay. Okay, so right, we know this. Wait, we know that. Okay, we know the voltage. Actually, we know the voltage, and so we want the VL. Okay, so another way we could do this is by KVL, Kirchhoff's voltage law, and so that would just mean in this loop right here. Here we'll define this. So positive, negative, positive, negative, negative to positive, positive to negative, negative to positive. We're gonna consider to be positive. Okay, so the positive direction, negative to positive. So this is going to be VR equals positive to negative. So really here, okay, let's explain this. Kirchhoff's voltage law means the voltages around a loop equivalent to 0 or sum to 0. So we're going to say VR minus VL equals 0. Okay, so therefore that would mean that VR equals VL. Okay, fantastic. So now we described the voltage. Okay, so now to further express this, we're going to say that, I guess we just say, so now we'll plug in this variable, because we want the derivative. I'm pretty sure we want the derivative. And then that's going to define it by the current, that's okay. Yeah, I think that's fine. Okay, here, let's see where this takes us. We're going to play it out. This minus VR L minus VR equals 0. Okay, but we could also call it, we'll just wait VL, but we don't want that. We want this, I guess it'd be I times R. Yeah, that's how we define it. If we're going to define it in terms of current. Yeah, so that's okay. Okay, and then now we're going to want to isolate this di with respect to dt minus divide by L, because we want the derivative by itself. So it's going to be I times R over L. Is going to look like that, still equal to 0. And now the way these first order linear equations work is that we're going to assume that I equals A times E to the power of st, because we know the derivative of E to the power of st contains its original function. So it's always going to be in this form. The derivative of this equals A times S E to the power of st. So it contains its original form, even though now we've multiplied by that which is in the exponent. The coefficient in the exponent, because t is our independent variable, this is what we're defining things by. Okay, so yeah, that's why we're gonna assume this form of the function. We're gonna assume this answer. So now if we plug this in, we're just gonna go ahead and jump a step. We're gonna pull out the a, we're gonna pull out the e to the power of st, and we're just gonna say, and then for the derivative itself, we're gonna label that as s minus r. Man, should I take you through everything, or we're just gonna jump through it? If there's anybody watching, I could actually ask and see if you care to do that. But there's not. There's absolutely nobody. Bruv. Yeah, I guess I gotta get back on X. At least I got people watching me on there. That's crazy. I ain't got a single person. I went through all this and I ain't got nobody. Whatever, I guess I can edit the video and post it to X. I'll see how that does in comparison to streaming on X. Okay, so S minus... minus R over L times E to the power st equals 0. S minus. Okay. That's supposed to be plus. That is supposed to be plus. Shit, we're flowing that way. I guess should be flowing that way. Positive, negative. Okay. Yeah, definitely plus. Okay. Anyways, continuing forward, S equals negative R over L. I feel like it should be L over R too, not R over L, but this is what we got. Okay, we're just going to see how it plays out. You know, I might be wrong. I'm pretty sure it's R over or L over R, but this is what we got right now. Okay, so if we say S equals that, then we know that I L of T equals A times e to the power of negative T R over L. Okay, so it's going to look something like that. I really feel like it's supposed to be L over R, but that's obviously not what we would get. You know, that's obviously not what we would get. Okay, so now A is going to be defined by our initial conditions. So now we figured out what the exponent is, and now we're going to define A by our initial conditions. I know IL of 0. That's why I wanted it equals lambda over L. Wait, so IL, can you see this end? Yeah. Wait, so IL of 0, that's at the time of the impulse, equals lambda over L. That is true. That is true. So that's what we put. And then we also have, okay, wait, so we just solved our okay, so this is our non-homogeneous solution. IL of T equals lambda over L times e to the negative T R over L. I really think it's L over R, but whatever. We'll see how it plays out. Now we got to solve for our particular solution because our final solution is the combination or the sum of both. Our particular solution is, wait, and so is that why that should have been negative? Maybe not. And then our particular solution is just going to be weird. It's going to be IR equals, I guess. No, it's not. We don't have a particular solution, do we? We don't have a particular solution because we don't have a drive. It's only the non-homogeneous solution. So if that were the case, okay, let's just plug in some numbers. Let's see. If that were the case, this would be 1 divided by 5e to the negative 3. Can you see that? Fucking barely. Times e to the power of negative 0.001, that's 1 millisecond, times our resistance of 10 ohms divided by 5e to the negative 3. Now that's our current. Okay, wait, no, this is correct. Okay, so 20 here, let's write it down. This equals 27.07. We're going to round amps. Yes, amps. So now we figured out our current, and again, we have, you know, both components experience the same current. So this is our current at 1 millisecond after the impulse had occurred. Then our voltage, VR1 at 1 millisecond. I should have wrote that here. Well, no, actually, maybe not. Yeah, that's okay. At 1 millisecond, VR1 at 1 millisecond is going to equal 27.07 amps times 10 ohms. And so this is going to be VR1 at 1 millisecond equals 270 call it 7. 270, we'll just say 270. That's fine. 270 volts. Yeah, okay, 270 volts. And that is correct. All right, so that was a little insight into a first order linear differential equation. And then because this was our model and we didn't have a source, we found we only needed to find the non-homogeneous solution. If there was a drive or a source, like right here, if this was included in our model, then we would have to find the particular solution in addition to the non-homogeneous solution. And then the final solution would be the sum of those those two, the particular solution and the non-homogeneous solution. So we'd have to add them together in order to get the final result. All right, well, very well. Okay, came to a conclusion on that one. I ain't gonna lie, I guess nobody's even watching anyway, so I'm gonna use the bathroom. Wait, I'm gonna keep that up. I'm gonna get rid of right here. We just go here, like that. 1 second. Okay, check. We're back. All right, well, so that's the answer to that. That's the voltage across R1 at t equals 1 millisecond. What is the value of the capacitor voltage at t equals 0 positive, just a moment after the impulse had occurred? Okay. Yeah, so this is going to be defined by just a moment after the impulse had occurred. What is the value of VCT at t equals 0 positive in volts? Okay. I think we can model this in the same way, right? It's just gonna be a resistor in parallel with this capacitor. Okay, now we have the application of the impulse. The capacitor is gonna look like a short circuit because initially the capacitor looks like a short. Initially the inductor looks like an open, and then as current or charge is deposited on the plates of the capacitor, it will build up in voltage and decrease in current flow. As the magnetic flux builds up in the inductor, it will begin to allow current to flow and the voltage across it will decrease. So, looking at the capacitor, we have the impulse, and all of the impulse is falling directly over the resistor because the capacitor acts as a short. So if all the impulse falls over the resistor, we're going to have the impulse itself, which is 1 volt second. Here, I'll write that in a different way. 1 volt second. And then this is going to be divided by R2, which is 10 kilo ohms, which is 10,000 ohms. 10 kilo ohms. And this will give us our current, remember, referencing Ohm's law. This will give us our current. So if we do 1 divided by 10, 1,000. Okay, so 1 e to the negative 4. Or 10 milliamps. So that's how we'll write it. We'll write 10 milliamps. So 10 milliamps is our current flowing like this. We have 10 milliamps, and we want to know the voltage across VC. So VC, that would be the constitutive. So VC equals the charge divided by the capacitance. And so our charge as of now, the charge deposited is determined by, so the impulse across the resistor determines our current, and the current is proportional to the charge. Charge actually equals, so Q actually equals the current over time, or like the current with respect to time. But since we have an impulse and things are happening instantaneously, we can simply define the charge as being directly proportional to I, because things are happening instantaneously. We're not really taking time into account considering this impulse response. So if this is true, then we can just say that 10 milliamps divided by our capacitance of 33 nanofarads, which is going to be 33 times 10 to the negative 9. That's nano. Okay, so let's go ahead and calculate that. 10 e to the negative 3 divided by 33 e to the negative 9. That's, 10 e to the negative 3. Oh, e. Wait, what was our answer before? 1 e to the negative 4. Did I do that wrong? No. Yeah, I did. It shouldn't be 10 milliamps, my bad. It should be 0.1 milliamp. 0.1 milliamp. Okay, so let's just write it. 1 e to the negative 4. That's a 0.1 milliamp divided by 33 e to the negative 9. Okay, that's our answer. So the voltage across the capacitor at 0 positive, just a moment after the impulse, is 3030 volts. Okay. So you see this phenomena that occurs when we do an analysis with an impulse input, or like the impulse response. Look at the crazy results we get. Our impulse was simply 1 volt second, but it happened instantaneously, and this is going to cause these kind of responses. Okay, so that's our answer for the voltage across the capacitor at t equals 0 positive, just moments after the impulse had occurred. Okay, what is the value for VC at t equals 1 millisecond? Right, okay. So similar to how we define the inductor by its current, we're going to define the capacitor by its voltages. This is just the way the things operate because a voltage or a capacitor stores energy in an electric field. AKA voltage field, or like, I guess you can't really consider it that. It's wrong to consider that, but an electric field, and it has this direct relationship to voltage. And an inductor stores energy in a magnetic field, which has this has a direct relationship to the current. Okay, so this is kind of the way that we go about expressing things. So if that's the case for VC at time t equals 1 millisecond, so let's go ahead and define this with our first order linear differential equation. Yeah. Similar to how we did over here. So we have trying to think, what's the way that we want to describe it? By the current? Yeah, we'll describe by the current. So we have IC plus IR equals 0. Okay, so now we're going to plug in our constitutive law for the capacitor, which is this: IC equals C times the derivative of the voltage VC with respect to time. Okay, so doing that, we'll write it all out. C times dVC with respect to time, plus we're going to write, in correspondence with Ohm's law, we're going to define the current through the resistor by its voltage and resistance. So this would be we're going to label it VC because they're the same, they're equivalent. VC divided by R equals 0. Okay, again, we want to get the derivative by itself. So dVC with respect to time plus VC divided by RC. Okay, and again, we're going to assume the solution of e to the power of this coefficient s and the product of this coefficient s in time. So here, I'll write it out. And there's inherently going to be some coefficient in front of the exponential function. That goes deep into the logics of mathematics. I'm near the point of being able to explain that in simple terms, but honestly, I'd have to really think about it. Maybe that's something I should do. I should sit down and really think about that, really come to an understanding, because the mathematics is what makes this shit possible. Ain't gonna lie. Mathematics is what makes it possible. Man, how we gain nobody. Absolutely nobody. Yeah, I don't know what to do about that. I guess I'm gonna have to get back on to X. I feel like this was really good. I mean, this is going to be a good stream, too. I feel like, so that really sucks. Okay, but anyways, this is where we are. Okay, so we're going to just go ahead and pull the similar terms out, and we're going to put our derivative as S, 1 over RC, times e to the power of ST equals 0. Therefore, S equals negative 1 over RC. Okay, we'll plug that in now, and then by initial conditions, we'll find our coefficient. And so VC of t equals AE to the power of negative t divided by RC. Yeah. Okay, negative t divided by RC. Okay, and so VC of 0 is it's just 1 volt. Yeah, it's just 1 volt. Because we had the 1 volt second impulse across here, and with these two being in parallel, we'll put our ground for reference. With these two being in parallel, they're going to share the same voltage. Okay. Yeah, so that's what we'll do. So VC, wait, is this the time analysis, right? We're going to do 1 millisecond? Yeah. So VC of 1 millisecond equals, no, there shouldn't be that. equals 1 times E to the negative T divided by RC. Okay, so we're going to go ahead and plug that in. We'll see what we get. We'll see if this is accurate. So we're just going to skip the 1. We're just going to go straight to E to the power of negative 0.001 divided by, and then parentheses, R, which is 10 kilo ohms, 10,000 times C, which is 33 E to the negative 9. That's incorrect. That's incorrect. One, right? 10,000 times 33 E to the negative 9. That's correct. Nanofarads. 0.001. Okay, so what we do wrong? What did we do wrong? Is it the initial voltage? No. Equals 1 volt. 1 volt. Okay, wait, that's not what we need to define. Okay, wait, actually, so no, let's say, here, let's write this all out. Actually, that's not even true. That's not true. The initial voltage is going to be 3030, isn't it? Defined by the current and the capacitance here. VC equals this. So VC of 0 equals, yeah, let's say Q over C times E to the negative T divided by RC. So that's accurate, and then that obviously equals 3030. So that's, I think, what we need to use. So let's put this back here. We'll plug that in. 3030. Whoops, come on. 3030 times E to the power of negative 0.001 divided by 10,000. Right, 10,000 times 33 E to the negative 9. 146. Okay, that's our answer. That's our answer. So VC of 1 millisecond equals, so that's the voltage across the capacitor after 1 millisecond has passed. 1 millisecond after the impulse had occurred. And we're going to have 146. Yeah, leave it there. Volts. Okay, so it's obviously a decay. Obviously, the impulse occurs and we instantaneously have 3030 volts across the capacitor. 1 millisecond later, we've decayed down to 146 volts. Eventually, it'll decay down to 0. And same as the inductor. I guess we looked at R1. We didn't look at the inductor, but we looked at R1. Man, I can't even show this whole paper. Here, let me zoom out a bit. Configure video. There we go. Apply. Okay. There we go. Now we can show everything. Fantastic. Okay, and now we define the other circuit, the RL circuit, by the voltage across R1. So let's take a look at that again. We initially had 2,000 volts over R1, and then 1 millisecond later, we decayed down to 270 volts. All right, so there you go. There you go, ladies and gentlemen. And that is how you do, that is learning electronics. Let's see. Exploring impulse responsive capacitor and inductor time analysis of MOSFETs with parasitic capacitance and first order linear circuits. We still have yet to get into the MOSFET analysis, but to be honest, I think I'm going to end it here and then I guess rebuy my subscription to X Premium. Like, bro, it's $40. It's not a lot of money, but fuck. Not a lot of money, but for real, I don't want to do that shit right now. I don't want to spend that money right now. I can't believe they took it to 40 anyways. It was at 16. Maybe did they... Maybe that's why. Nah. Used to unlock deep searching thing. Creator hub. See, that's at $4. That's at 11. Starting at 50. Bruh, what'd they put me to? Nah, they must have had me on like one of the higher subscriptions. Ain't no fucking way. I mean, see, starting at $11, I can definitely do that. Write articles. Oh, I just can't write articles with it. I just want to be able to go live. Bookmark. X Pro Media Studio. Monetize, yeah. X Pro, powerful real time. People who live on X monitor multiple timeline on a single. Analytics, blah blah blah. Unlock deep search, early access, radar. What's radar? Real time trends like never before. Whatever. Download videos, edit posts. Wait, what about? Can I go live with this? Customization, creator hub. Build annually. Per year, build monthly. Alright, yeah, I'm gonna end it here. Alright, cool. Thanks for tuning in, guys. I think I'm gonna work another problem, but I'm gonna hop on X.